I think he'll come back soon, but not today, obviously. And so this may be the last time I talk to you guys. I mean, maybe Dr. Skimbordas will be back Tuesday. I don't know. Maybe he'll be back tomorrow. I'm not sure. All right. But it does seem like you guys have a test early next week. I'm guessing Tuesday you guys have a test. Now, what's exactly on that test? You can ask Dr. Joseph tomorrow. Although I should probably talk to him about it. But I'm assuming it would be on the things you've already covered in this class, right? Yeah. That would probably be likely, which is what? Like vectors, lines, planes, that kind of thing, right? Dot product, cross product, guessing. Okay. So I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, we pray for Dr. Skimbordas that he would be back here again safely soon. And we just thank you again for your many blessings to us. And just ask you to bless this class, Lord. In your name I pray, Lord Jesus. Amen. All right, so I know Dr. Joseph introduced calculus of paths to you guys last time, right? And to summarize, if we have r, which is a function of time, right? And it is x, which is a function of time, y is a function of time, z is a function of time. This is a weird thing. Since you guys aren't my class, I complain to you. Why are you taking out your notebooks now? Like, what did you think was going to happen? Right? So this is the way to win friends and influence people, right? Like, it's out of the gate. But I don't know. This has been a pet peeve of mine since I was a student. Like, I would sit down and then I'd watch everybody getting the stuff out of the bag and be like, why not? Anyway, of course I do the same. But okay, so after he talked to you about the limiting process and all that, what did we learn? What's dRdt? Very simple. What is it? It is, yeah, we do dx dt, dy dt, dz dt. Simple as that, right? And by the way, this has a name. If we're thinking of r of t as being the physical position of some object, in physics this is called the position at time t, right? So if r is the position, then that would make this the velocity, right? If you were to calculate another derivative, right? You can do it again, and that would give you the acceleration. Yeah, good. So both velocity and acceleration are actually vectors, right? And so in physics, the usual notation for this is like v, and the usual notation for this is like a. A is dv dt, all right? Great. These things are true. Another thing I should share with you is that the magnitude of v is v, right? And so v would be equal to the square root of dx dt squared plus dy dt squared plus dz dt squared, right? If we're in 3 dimensions. And great. So you can calculate s at time t, let's say, is the integral from t naught to t of, well, v dt. So this will give you the arc length of the path. In physics, you could think of this as being the distance traveled. All right? Now, I'm gonna leave this. I think Dr. Joseph might like to lecture on this tomorrow more, so I'm gonna leave that for him, okay? Because it's a good thing to do for a whole hour. And so I'm gonna leave that for him. We'll circle back that tomorrow probably. One of the things I wanted to share with you is just an application of the derivative. So the first application, definition, let me give you a definition here. The tangent line so let's say the path is r maps to r of t. So that's just a fancy way of describing, oh man, well that's just nuts. Let's trade that r for a t. Okay, so pictorially what's going on here is maybe you got some real line, right? And what are you doing? You're taking it and you're you got some path, right? You basically think of the path as a formula to take the real line and then stretch it out in space over here. Like, so a typical point here, that would be in particular r of t naught. Sorry, poor font choice on my size. I should have made that bigger. I hope you guys can see it. If not, you should have brought binoculars. Sorry, I forgot to announce that. Anyway, so that's a curve, right? A path is, basically r is the function which goes from here to here, right? So in other words, r is a function from, let's say the reals to R3 for us in the moment. This is a path, all right? So what's the tangent line to this path at, continuing my sentence up here, at r of t naught has direction vector r prime of t naught and parametrization, we could say L vector of t equals to r of t naught plus r prime of t naught times t. All right. So let me give you a specific example of this. So example 1, perhaps we've got the path r of t is equal to, let us look at 2 cosine t, 2 sine t, and, I don't know, t. All right. Let's find parametrization of tangent line to path at r of, let's do r of pi. Right. So what would the point r of pi be? I'm recording this lecture, guys, because a couple of reasons. Number one, I just usually do, and number two, now Dr. Skimbordas can see what we're doing, and he'll know what I covered, and he'll know what you'd test you on and stuff like that, right? So, anyway, r of pi. So you just plug in pi, right? And what does that give us? -2, 0, and pi. All right, great. Now, what's the velocity for this curve? What's dr dt? -2 sine t, right? 2 cos t, and 1. All right. So then, what is r prime of pi? We got 0, -2t, and apparently 1. Right? Evaluating 1 is kind of silly. Yeah.
Why do you keep the t?
Oh, yeah, sorry about that. Good, you guys are paying attention. Woohoo! So, excellent. I do appreciate corrections, especially when I make mistakes, which I will do. Okay, so then what? Thus, the parametrization is equal to, here we go, -2, 0, pi plus t times the vector 0, -2, 1. Right? And then if you'd like to simplify that, of course you can add things together. What you got? You got, -2, comma, -2t, comma, pi plus t. So there you go. That is the vector parametrization of the tangent line at that point. Now sometimes we're interested in finding what's called a colliding tangent line. Do you guys know what it means for two paths to collide? Yeah, they bump into each other. So what is collision? What is collision of, say, path R1 and R2? What's that mean? Versus what's intersection? What's the difference between collision and intersection of two paths? Can you guys give me the, what would you need to look for? For a collision, what you would need is that R1 of t, let's say t, let me call the collision time t boom. There we go. You need R1 of t boom equals to R2 of t boom. Not a very terribly useful variable name, but there it is. So when the collision happens, it's the same time, right? What would the criteria be for the intersection of two paths? Possibly different time, right? So you could have R1 of like T1 equals to R2. What I usually do is put a T here and I put an S there. So like to find intersections, I put T as the parameter of one path, I put S as the other parameter of the other path, and then I try to solve the X, the Y, the Z equations being equal for different possibly values of T and S. Intersection is weaker than collision, right? You can have paths which intersect, but do not collide. So, question, does this tangent line, does it collide with my path at pi? Does R collide with L at t equals to pi? Well, it doesn't, right? Because what's going on here? If I can foolishly attempt to graph it, what this thing is called a helix, all right? So the graph of R looks something kind of sort of like this, all right? That's a very, I mean, I'm starting with t equal to 0 here, okay? This is, you know, R of t. So R of pi is, I think it's like back here-ish, right? Well, we had it. It's 0, -2, 1, right? Roughly speaking. And what's L look like? Well, you know, pictures of three-dimensional lines are always a little bit sketchy, but it's a tangent line, right? So it should look something kind of like that, you know, roughly speaking. And the thing is, that point right there is what? That is L of 0. See, L of 0 is equal to R of pi. So as I have it currently set up, the tangent line collides with the path, but it intersects the path, right, at the point of tangency, but it certainly doesn't collide. Can you guys tell me how to write down the equation of the colliding tangent line? How would I get the colliding tangent line? What would that, let me call that, I'll call it L for line collide. What's the formula for that? I'll start you out. -2, 0 pi plus something times 0 -2, 1. What, fill in the blank for me. What should I put there? Pi? Well, it needs to be a function of t. What's that? T minus pi. And that's it. So if you want to write down the colliding tangent line and simply replace t with t minus t naught, that will give you the colliding tangent line, right? Now, if you're actually writing this tangent line to like describe the motion of some physical system, right, and t is actually meaning time and it's not just a parameter of some path, maybe using the colliding parameterization would be more wise because it would give you something you're actually interested in. So I just wanted to share that with you guys because I asked Dr. Joseph if he talked about the tangent line last time. He said he didn't. Quite, well, he did, but he didn't. And so I thought that would be a good place to start, just to get us warmed up. Oh, here's a follow-up question. Where does this helix intersect? Let's think about intersection of the helix. Two questions. Where does helix intersect? Let's see. First of all, z equals to 4, and then part B, the plane x plus 2y minus z equals to, oh, I don't know, 2. I may regret that. I just made it up. It might have infinitely many answers. All right. How do you find where a path intersects one of the things you guys have already been talking about, right? Like a plane, for instance. How would you figure that out?
We just set the z equal
Set the z part equal to 4. Excellent. That's exactly what you'd do. So I regret moving my camera. So yeah, we just put the z part equals to 4. So what's the z equation here? So like, it's sometimes helpful to unpack this in terms of the scalar parametric equations for the curve, right? X equals to 2 cosine t, y equals to 2 sine t, z equals to t. That's how to look at the path at the level of parametric equations, right? But remember, parametric equations are a package deal. They're actually just a shorthand for a vector-valued function of time. And okay, so yeah, like you guys just told me, I just put this equal to my my t, right? Z equals to t. So, oh, apparently t equals to 4. So r of 4 is, what is it? 2 cosine 4, 2 sine 4, 4. So that point right there, that's the point that this helix intersects the line, excuse me, the plane, z equal to 4. Yeah.
So why are we using 4? I'm just curious.
Oh, just to pick something.
Really?
No reason. Yeah. You could have, would you prefer z naught?
No, I mean, I was just wondering.
Check it out, yo. Just arbitrary. We could put a z naught here.
Okay.
And then that would put a z naught here. And that would put a z naught here. And then I put a z naught here. And that would put a z naught here. So there you go. Now we did it for all possible horizontal planes. It was the same work. But I didn't start with that because it would have weirded you guys out. But I do appreciate your question. So there's really no reason. I just picked 4. Just like you might ask, why did I pick the plane x plus 2y minus z equals to 2? No reason. Just to give us something that's got a little bit of, you know, texture to it, I guess. So how would you find the intersection? So what is this plane? I'll help you guys prepare for your test next week. What's the normal vector to this plane? You guys tell me? I heard a 1, a 2, a negative 1. All right, great. Those of you who said that with confidence, you're partly ready for the test. Those of you who did not know that, woo, yeah. You could work on that. Like this should require exactly as much thinking as was given by the people who said this. Not much, right? Okay, so anyway, where are we? So our x equation, y equation, z equation over there, so we just plug those into here to find the intersection of the path with the plane. So we're going to have to solve, and we may not be able to solve it because I just made this up. 2 cosine t, wait a minute. Oh yeah, 2 cosine t plus 2 times, don't be careful, there's 2 2's, right? 2 sine t, ugh. And then z is, oof, yeah, I don't like our chances here. Minus t equals to 2. So anyway, yeah, I'm not going to belabor that. That's not a nice equation. Like if I want to solve sine of t equals to a polynomial, I'm looking at some kind of numerical methods problem here. Yeah. So this, I mean, you could repackage this as the problem of finding 4 sine t plus 2 cosine t equals to like 2 plus t, right? So you can graph this and you can graph that. Hopefully they've got a solution somewhere. I think they do because the one is a sinusoid, right? So this side here looks something like this. And that side there, if I'm graphing y versus t here, that's got a y-intercept of 2 and it's got a slope of 1. So, you know, there's a solution somewhere. And I think there's probably just one, but if I hit this thing the right way, I guess I could conceivably intersect 2 places, but there's at least one time when this happens. To actually figure that time, I'd have to get a computer out and do stuff, all right? So this would be a very unfriendly question for a test, right? Yeah. All right, well, that's what I wanted to tell you guys about that. So, ooh, excuse me, I try to use my eraser shirt. Here. Doo-doo. So you guys like Calc 3? I love Calc 3. I think it's like the most interesting calculus probably. It's also so different than Calc 1 or 2. You know? Like geometry plays such a bigger role here. You know? There really isn't much geometry in Calculus 1 or 2, is there? You know? So, I want to talk to you guys about the geometry of curves here in the time that remains. So I'm going to introduce you guys to something called the Frenet frame. And before I just drop the formulas on you, I want to explain to you the idea of the method. So this is the Frenet frame. AKA the TNB frame. All right? And essentially the goal of this whole discussion is to develop a structure which detects when two curves are congruent in the sense of high school geometry. What does it mean to be congruent in the sense of high school geometry? Do you guys remember? You're like, I didn't have high school geometry, so shut up. That's the case for a lot of people now, right? But so two curves are congruent. Like two triangles would be congruent means what? They have the same size and same size and shape, right? Same angles, same side lengths, right? Similar triangles are not congruent. For example, they don't have to be anyway, right? So the question of congruence is basically the question is like, you know, I've got some wackadoodle curve in 3 dimensions. It looks like that, right? And then I've got another curve in 3 dimensions, and it looks like that. Are those actually the same curve? And just one has been taken from here and moved over to there and rotated and shifted. Are those the same curve? How would you decide? Right? So once we completely understand the Frenet frame, it gives us a set of tools to answer such questions. And it also will give us a much more deep understanding of the structure of, say, velocity and acceleration and their relation. So it's a twofer. So let me get just straight into it. And also, it will give me a chance to showcase some of the rules you derived with Dr. Joseph last class, like the dot product, like the product rule for the dot product, or the product rule for the cross product. You guys did that, right? Yeah. So, or the product rule for scalar multiple of a function times a path, yeah? All these things. So, rather than dropping the formulas on you, let me just first try to just kind of graph what the TNB looks like. All right, so T is pretty simple. T is going to be the unit tangent vector. And this is the one sole time in Calculus 3 that I don't put a vector on the vector. Pretty much I always put vector on a vector, or I put a hat on a unit vector, right? Well, how would you know? You haven't had my class. But I'm guessing that's probably Dr. Scambordis' convention as well. Sorry, I have to get some markers. So the unit tangent should point, well, we already know what that does. It points in the direction of the curve, right? So like the unit tangent would look something like this. All right? And we call that T, the unit tangent. Then, so let me draw it another place here. And I'll try to draw it another place here, all right? I'm trying to make these all the same length. I may or may not be succeeding, but there we have it, okay? So T, the unit tangent. Then you can define something called the unit normal, all right? Or sometimes called the Frenet normal. Frenet is some dead mathematician who discovered this stuff, all right? But N looks like this. It's perpendicular to T. Also length 1 vector looks that. Like that. And so N, which way does N point? If you can imagine putting a circle that just kisses the curve, it's called an osculating circle, right? Osculating is like some ancient forgotten word for kissing. So don't let me catch you osculating in the hallway. I mean, I'm just kidding. I really have no power. If you were, there's nothing I could do except go, ew. I mean, I would find it cringeworthy, and I would go on with my life. But Anyway, so the osculating circle you could just imagine fit. I don't even want to draw it. I'll draw one. No, I don't want to. I'm going to draw down here. Let me just. It's easier to draw the osculating circle in a plane. So, osculating circle would be like this, right? If the curve gets tighter, then the osculating circle gets smaller, right? So it just fits just into the radius of curvature, if you will, whatever that means. What is the radius of curvature to a curve? Because you use that term like it means something. We're about to define it. Okay. So these are the osculating circles. So the normal points towards the center of the osculating circle. All right. So N and T are constructed to be perpendicular. If we want a third vector, which is also perpendicular to T and N, what do?
Cross product.
Cross product, right. So T, right hand, crossed into N, points in the direction of your B. So B here is like into the board. What's their symbol for into the board? Something like this, maybe? I don't know. B is into the board. Here, let me draw it in perspective so it's easier to see. Kind of like this, all right, so like that. Oh man, I can't draw into the board worth anything. Rats. Poor planning on my part. However you want to draw into the board. I guess I'm going to go, maybe this kind of, you can kind of see it like that. I don't know. Let's see here, T cross N, again into the board. So I'm going to kind of picture it like that if that makes sense to you. If it doesn't, I'm sorry. Here, T cross into N, something more like this, all right. Okay, so what are the formulas? Definition. The unit so given. So here's the fine print. Given a non-stop, non-linear path, let's say R, we define T equal to 1 over the speed times the velocity vector, or if you like, specifically I'm saying 1 over the length of dr dt times dr dt. All right, that right there, my friends, is going to give you the unit tangent. That's the unit tangent vector. It's just the normalized velocity vector. That's all it is. Then the normal vector is actually going to be given by 1 over the length of the derivative of the unit tangent, also known as dt dt, times dt dt. So it's the normalized derivative of the tangent vector. All right? And then, well, B, the binormal, is T cross N. So tangent, normal, binormal. Okay? Let's calculate these for the helix. I'm going to make the helix more interesting. I'm going to do the helix with some parameters in it just for more fun, if that's okay with you guys. Why does this class have to be at 8:15? Ay, ay, ay. All right, so let's give this helix a radius r and a slope m, and I'll keep it in more or less the kind of standard form. So this is example 3, I suppose. R of t equals to, let's say, r cos t, r sine t, mt. So I would say this is a helix with radius r and slope m. Now, all right, so let's get to it. Let us calculate dr dt. You got yourself minus r sine t, r cosine t, m. Now you guys calculate the speed for this curve. What's the magnitude of the velocity here? What we got? So we calculate dr dt dot dr dt, right? What's that give us? R sine squared t plus r cosine squared t plus m squared, also known as r squared plus m squared. Was there a question? Did I do something? So, okay, that's the square of the magnitude, right? So what's the speed? So apparently the speed, v, is the square root of r squared plus m squared, right? So incidentally, this is what's called a constant speed curve, right? Or constant speed path, because the speed just depends on the parameters r and m. That's kind of neat. What's the unit tangent? So the unit tangent is, again, the velocity divided by the speed, which in this case is 1 over the square root of r squared plus m squared times minus r sine t, r cosine t, m. So there you go. That's the unit tangent to the helix. All right. Now let's calculate the unit normal. So to calculate the unit normal, which I'll do in purple, we must calculate dt dt. dt dt, well, that constant, let's leave it out front, you know. No need to bring that inside. Why write something 3 times when you can just write it once, right? And we've got, you know, minus r, the derivative. Actually, do I need to write this out? Let me just do it. What is the derivative? I think this one's dead. I heard a negative r cos t minus r sine t and 0. Excellent. So factor this thing out. We've got actually r divided by the square root of r squared plus m squared times the vector minus cosine t minus sine t 0. Pro tip. Sorry, I'm an idiot. If you have a vector a, if I won't laugh at it, somebody who will. So a is equal to a times its unit vector, right? So if you can write a vector, that's unique, by the way. If I had this was equal to, you know, b times some other unit vector, that would force the magnitudes to be equal and the unit vectors to be equal, right? In other words, a vector is specified by a magnitude and a direction. The direction, of course, we can encapsulate by a unit vector, because in 3 dimensions, a standard angle is not enough, right? So anyway, let's look at this. We've got, this is a positive quantity, right? Agree? This right here is a unit vector, right? Yeah. What is the normal vector by definition? It is the normalized derivative of the tangent, unit tangent. So that tells me, without further ado, that the normal vector, which is, by the way, you know, dt divided by the length of dt dt, is nothing more than that guy right there. So if you do it right, your normal, quote unquote, must be a unit vector. But there it is. This is the normal. Okay? Next, how about the binormal? B is t cross n, which is, we've got our 1 over the square root of r squared plus m squared from my formula. My t's got a minus r sine t, r cos t, m, and we're supposed to take the cross product of that with minus cosine t minus sine t. 0. All right. So what is that? Take the cross product. How does it go? So first of all, the constant out front is going to ride along. So we're going to have 1 over the square root of r squared plus m squared. All right. And then what do we have? Well, the x component of the cross product is obtained from, let's see here. Let me think about this. YZ, nope. So I believe I've got an m sine t for my first component. For y, let's see here, minus m cos t and then for z, I've got r sine squared plus r cosine squared, so I just get r. You're like, that's kind of sketchy what you just did. You didn't really write down your work, did you? Well, that's true. I just thought about it. But the good news is we can check our answer because this is a cross product, right? So if this indeed is the binormal, right? If that is the binormal, what must be true about it? It must be perpendicular to what? Both t and n. Is it? Or did I make a mistake? So when you take the dot product of this, we get a minus mr sine squared minus mr cosine squared plus mr, also known as 0. Because sine squared plus cosine squared is 1, we get a minus and a plus, cancels. And then the binormal dot with the this one is more obviously 0 because you get like a minus sine cosine and you get a plus sine cosine, both with the same constant. So dot products are both 0. I calculated correctly. Woohoo! So there you go. That is the TNB frame for the helix. This is a nice problem to put on the test because it tests a whole bunch of things that we're interested in you guys learning to do. Differentiate, take cross products, rescale things, calculate magnitudes. It has so much goodness. So, all right. Now, if that's all there was, I guess it would be interesting, but that's actually not the most interesting thing about all of this. The most interesting thing is that we can also use the TNB frame to define something called the curvature and the torsion. All right? So, since I don't have too much time in here, I'm just going to go ahead and give you the definitions of those. And then I'll show you how it works. I usually define the curvature and torsion in terms of the arc length parameterization, but since Professor Joseph's going to be talking to you more about arc length tomorrow, I think I'm going to forego that and instead give you the definition in terms of what's called a curve which is not necessarily parametrized with respect to the arc length. And so here's the definition. Definition. The curvature, which we use a little kappa, is equal to 1 over the speed, all right, times the magnitude of the derivative of the unit tangent with respect to time. That's curvature. The torsion is defined to be minus 1 over the speed times the derivative of the binormal dotted with the normal. All right? So this is curvature. This is torsion. Generally, they're functions of time. All right? what I think is interesting is we can actually prove that the change in the tangent and the normal and the binormal, as they change, as we go from point to point on the curve, if we study the time evolution of the Frenet frame, we'll find that the way that the T, the N, and the B sort of rotate into one another, it's all specified by the curvature and the torsion. All right? By the way, no one asked me, but if you're wondering why it has to be nonlinear, it's because if you think about a line, well, it's easy enough to find the tangent, right? But then which direction is the normal? Like this one, or this one, or this one, or this one. See, there's just too many. There's a degeneracy here. This is unnecessarily sophisticated for lines. Lines are simpler than this. So we don't treat lines with this. However, there is a limiting sense in which you come to a line. So the curvature, by the way, also is reciprocal to the radius of curvature. So you can define the radius of curvature r, which, not to be confused with that, I'm going to use a little r. There's no standard notation for it, but like the radius of curvature is 1 over kappa. And it turns out that this curvature is exactly reciprocal to the radius of the osculating circle that I was talking about. All right? So I'd like to use some of the calculus that Dr. Joseph shared with you last time to derive the Frenet-Ray equations for you. All right? Now I'll probably get stuck, but actually before I do that, because I'm probably going to use this whole board to do that, let us go ahead and calculate the curvature and the torsion for the helix. Let's just do that to start with, right? So we already know that the speed v is, what is the speed? We figured it out. Square root r squared plus m squared for the helix, right? What's the magnitude of d t dt is what? So I'm working on calculate curvature and torsion. That's what I'm doing. All right, so the curvature 1 over v magnitude of dt dt. Great. V, so that's 1 over the square root of r squared plus m squared. Where's my dt dt is? It's right here, right? Oh, the magnitude is what I boxed here, isn't it? That is the magnitude of dt dt. So the curvature is r divided by r squared plus m squared for a helix, this helix. It's kind of cool. How about the torsion? Let's calculate dB dt. What's dB dt equal to? So we've still got 1 over the speed, right? Oh, fine, I'll just write out 1 over the square root of r squared plus m squared times what? When I differentiate this, I get what? M cosine t and m sine t, okay. And 0. All right, great. So then what? I need to do what? I need to take the dot product of dB dt with what? I'm supposed to take the dot product of dB dt with the normal. That's part of how to calculate the torsion. So let's take the dot product with the normal. What do we get? Oh man, look at this. I'm putting a vector on the normal and I'm putting a vector on b. Come on. That is violating my notations in here. I'm sorry, guys. Anyway, they are vectors. You're like, isn't that inconsistent with your larger program of magnitude unit vector notation? Well, yeah, it is. I just custom. Nothing if not inconsistent, right? But so dot with n here, what'd you get? We get this constant out here, right? And then we've got a minus m cosine squared t minus m sine squared t plus 0. But that is just what? Sine squared plus cosine squared. Man, if you don't know sine squared plus cosine squared is 1, you're in a lot of hurt here. You guys know that. All right, so I get minus m over r squared plus m squared. So my torsion, finally, is minus 1 over the square root of r squared plus m squared times minus m over the square root of r squared plus m squared. The minuses are canceling, and we get m over r squared plus m squared. So there's your torsion, and there's your curvature for the helix. What'd I do? Is it behind my bag or something? No. Are we good? Oh, it's not me. Okay. So some fun things to think about. The helix, right? What would happen for a helix if you have a helix, right? And it's going, right? What if you put m equals to 0? What would that be?
Just a circle, like a 2D circle.
Yeah, just a 2D circle. So what's the curvature for a circle? If m equals 0, we get what? We get curvature is r over r squared, which is 1 over r. Good. I told you the curvature was reciprocal to the radius of curvature. It had better be the radius of curvature for a circle if this is going to be in any way consistent, and it is. Yay. How about torsion? What's the torsion in the context of a circle? 0, right. What does torsion being 0 tell you, generally? This is not the easiest thing to actually prove, but if you start understanding these things geometrically, you should start to realize that the torsion being 0 forces the curve to be planar, which means that the whole curve is in some plane. See, the torsion being 0, if you look at it from the perspective of this well, I need to derive some equations. Once I derive those equations, it becomes a little bit more obvious. But yeah, the torsion being 0 means that the curve lies in a plane. The torsion being non-zero, what that means is that the curve, as it evolves, it's lifting off its plane of motion. So if you look at the plane of motion, it's spanned by the velocity and the acceleration vectors. They give you some plane, right? And so infinitesimally, the motion of the path is in that plane spanned by the velocity and the acceleration, right? If the torsion is non-zero, that curve is lifting up off the plane, all right? It's curving up off the plane. So there's that. Okay, so there you go. That's the Frenet frame, the torsion, the curvature. And this is most unpleasant to calculate. So, just some warnings about examples. If your path doesn't have constant speed, when you do this differentiation, the dt dt, you have to do a product rule. You get one piece from the derivative of the speed and another piece from the derivative of the, the other piece. You get a product rule. It gets much messier, all right? And actually finding formulas for the curvature and the torsion, they can be prohibitively difficult. My brother, also a mathematician at Appalachian State, he once invented a curve. Basically, it's just a curve that wraps around a donut, if you can imagine that kind of thing. And he uses a program called Maple, which is like Mathematica, but cheaper. Well, it used to be cheaper. I don't know anymore. But anyway, the formula for the torsion is something like 50 pages as a PDF. All right, so it is possible. It's possible for these formulas to get quite out of hand quite quickly, but the helix makes a lovely test question. All right. So, something to think about. If you have 3 vectors, right? When can you take those three vectors and build any other vector from those three. Is it always possible? If I give you a vector v, a vector w, and a vector u, let's say, can you build any other vector from v, w, and u? Yes or no?
Not if they're all the same vector.
Let me, yeah, not if they're all the same vector. Let me do a, b, c, because it's easier to talk about. So I've got like a, I've got b, I've got c, right? Can I make v equal to like c1 times a plus c2 times b plus c3 times c? Is it possible to solve that equation for any v for a given choice of a, b, and c? Already one of you said no. If my vectors are in fact the same vector, I only get things along the direction of that vector, right? What if two of them are different? Well, that's not enough either, right? If all three of these lied in a plane, if they were coplanar, you wouldn't be able to obtain all vectors, right? But a simple test would be, for example, if the triple product of a, b, and c was non-zero, that would mean that they're not coplanar. Do you guys know what the triple product is? You guys talked about that? No? So if we do a dot b cross c, this is equal to plus or minus the volume of the parallel piped with sides A, B, C. You should have had homework on this. There is homework on this in your book. You should look at it, find it, it's there. It's not a big deal, right? You take the cross product of two vectors, you take the dot product of the other one. That gives you plus or minus the volume of the shape which has A, B, and C as sides. If you think about that, right? So this is A, this is B. C maybe, I don't know, whatever. I can't, sometimes I can draw it, sometimes I can't, but whatever. Parallel piped. The volume of that is plus or minus A dot B cross C. Right, the reason for plus or minus is just because if A, B, and C are right-handed and you put them in the right-handed sense, you'll get a positive, but let me not belabor this point. Now, even if that's the case, if that's non-zero, generally finding C1, C2, and C3, it's a kind of a drag. It's a real pain, right? However, what if instead of A, B, C, we have X hat, Y hat, Z hat? Oh, my bad. You guys use I, J, K, right? So if I did that, if V is equal to, let's say, A, B, C, my bad, V1, V2, V3, what would I choose for A, B, and C, C1, C2, and C3 there? Like, what is V dot I hat? What's it equal to? It's just C1, right? Why is that? Because J dot I hat and K dot I hat are what? They're 0. So in short, if we have a set of vectors which are pairwise perpendicular in all length 1, it is most easy to calculate components. All right, so wait a minute, that's what we have with TNB. TNB is exactly such a thing. TNB is just like X, Y, and Z. They're unit vectors, I, J, K, because it's also pairwise perpendicular. So what this means then is that if we were to look at the derivative, which I'm going to start writing dd, if you guys don't mind, let me write that as t prime, just to save writing. So t prime we can look at as t prime dot t, t plus t prime dot n, n plus t prime dot b, b. And n prime we can look at as n prime dot t, t plus n prime dot n, n plus n prime dot b, b. And b prime, guess what, is b prime dot t, t plus b prime dot n, n plus b prime dot b, b. So this right here is the problem we'd like to solve. I'd like to figure out exactly what the values of these dot products are in terms of the curvature and torsion if possible. All right? So how should we do that? Like, how do you work that out? So on your test next Tuesday, if the question is, are these three vectors coplanar, what do you check? Triple product, right? Or if you want to find the volume of the parallelepiped, what do? Take the cross product of two, take the dot product of the other, right? Do you guys know determinants? If you do, the determinant, this is also equal to, straight up, the determinant plus or minus the determinant of, well, excuse me, just that's equal to the determinant. This is equal to the determinant of A, B, C. Just, or if you don't like columns and you like rows, guess what? The determinant doesn't care. The transpose of the determinant is the determinant of the transpose, so it's all good. That's a simple method you can use to calculate the triple product, if you know what a determinant is, and if you don't, whatever. All right, so, well, maybe you should learn, I guess. I don't know. I have other formulas I prefer for the cross product, but now, what do we know? The fundamental things we know that T dot T is equal to what? It's equal to 1, right? Do you guys agree? It's a unit vector.
Yep.
What can you tell me about the relation of the derivative of a unit vector to a unit vector? Differentiate that. See what you get. We need to use the calculus, which Dr. Joseph shared with you guys last time, right? So differentiating this, we got what? T prime dot T plus T dot T prime equals to 0. But the dot product is what? It's commutative, right? So T dot T prime and T prime dot T, the same thing. So what does this tell us? Twice T dot T. So this just tells us that T prime dot T is equal to 0. A unit vector must be perpendicular to its change. That makes sense if you think about it, because the length of the unit vector is not changing. So of course the change has to be in the perpendicular sense to it. Now that tells us immediately 3 of these things are 0, because if you can do this for T, we also know what? N dot N is 1, and that's B dot B, right? As well. So by the same calculation, we have that B prime dot B is equal to 0, and N prime dot N is equal to 0. So let's list our conquests. 0, 0, 0, right? We got those. Great. What else do we know? All right, so we also have the definition of curvature and torsion, right? So dt, right, is equal to, what is it? It's equal to, well, I'm sorry, let me just, this is the point where I'll get stuck if I'm not careful. Let me erase this stuff up here, just get out of the way. All right. So let's think through n, the definition of n. Right? N is what? N is equal to 1 over, what is it? dt, 1 over the magnitude of dt dt, right? Times what? Times dt dt, right? That's the definition of the normal, which I'm vectorizing for. Anyway, okay, we got it. I would point